Welcome to this coding walkthrough. In this session, we'll tackle LeetCode problem number 1668, titled Maximum Repeating Substring. This problem challenges us to determine how many times a substring can be repeated consecutively in a given sequence. Let's dive in and explore the solution step by step. In this problem, you are given two strings, sequence and word. The task is to determine how many times the string word can repeat consecutively within sequence. To understand this, let's consider word as a block that can repeat multiple times. For example, if word is ABC, the blocks it can form include ABC, abcap, abcapcap, and so on. We define the term k repeating to describe how many times word repeats consecutively. If word repeats exactly 3 times in a row within sequence, we say it's 3 repeating. Your goal is to find the maximum k for which word is a k repeating substring of sequence. If word doesn't appear in sequence at all, the result should be 0. The input includes two strings, sequence and word, both made up of lowercase English letters, and the output is an integer representing the maximum k value. The constraints ensure that both strings have lengths between 1 and 100. To clarify the problem further, let's look at an example. Suppose sequence is a bap and word is ab. Here, the substring ab appears twice consecutively within sequence. Specifically, it forms the block ABAB, which corresponds to k equals 2. Since ab is repeated 2 times in a row, the maximum value of k is 2. This example demonstrates how to calculate k by identifying consecutive repetitions of word within sequence. Now, let's consider another example where sequence is again a bap, but this time word is BA. In this case, the substring BA appears only once in sequence, without any consecutive repetitions. Since there are no repeating blocks of BA, the maximum value of k here is 1. This shows that even if word appears in sequence, it must repeat consecutively to contribute to a higher k value. In another scenario, let's say sequence is still a bap, but now word is AC. Here, the substring AC does not appear at all in sequence. When word isn't present in sequence, the maximum value of k is simply 0. This case highlights that if word cannot be found in sequence, no repetitions are possible, and the output should reflect this by returning 0. To summarize, the constraints of the problem ensure that sequence and word are both non-empty strings consisting of lowercase English letters. Some edge cases to consider include when sequence and word are identical. Here, the output will be the length of sequence divided by the length of word. If sequence is shorter than word, the output is 0 because word cannot fit as a substring. Additionally, if word appears in sequence but not consecutively, the result is 1. For the smallest possible inputs, such as sequence equals a and word equals a, the output is 1. Finally, if word is absent entirely, the output is always 0. These scenarios help you prepare for a variety of input cases while solving the problem. To tackle the problem of finding the maximum number of times the word can be repeated consecutively as a substring in the sequence, we start by analyzing different approaches. The brute force approach is the most straightforward method. It involves incrementally checking how many times the word can repeat consecutively in the sequence. For example, we start with 1 repetition of the word, then 2 repetitions, 3 repetitions, and so on, until the substring no longer matches the sequence. This can be implemented using a simple loop where we repeatedly construct and check longer strings of the word. However, the computational cost of this approach is significant. The time complexity is k*n, where k is the maximum number of repetitions and n is the length of the sequence, as each check involves constructing new strings and performing substring matching. Additionally, the space complexity is k*m, where m is the length of the word, due to the repeated creation of longer strings. While intuitive, this approach becomes inefficient for larger inputs. The brute force approach, despite its simplicity, has clear inefficiencies, particularly for large inputs, due to the repeated construction of strings and their corresponding substring checks. To address this, we turn to an optimized approach using binary search. The key insight here is that if the word repeated k times is a substring of the sequence, then the word repeated k1 times must also be a substring. This monotonic property allows us to use binary search to efficiently determine the maximum k. The process begins by setting binary search bounds. Low starts at 0, and high is the theoretical maximum repetitions, calculated as the length of the sequence divided by the length of the word. For each midpoint, we check whether the word repeated mid-times exists as a substring in the sequence. Based on the result, we adjust the bounds. If the substring exists, we move the lower bound up, otherwise, we reduce the upper bound. This method drastically reduces the number of substring checks needed compared to brute force. The binary search approach offers significant improvements in efficiency. Its time complexity is O log k asterisk n, where k is the maximum number of repetitions and n is the length of the sequence. This is because each substring check, which costs O n, is performed only O log k times, thanks to the binary search process. In terms of space complexity, the method is highly efficient, requiring only O1 additional space, as no extra data structures or repeated string constructions are needed. Alternatively, a sliding window approach can also be used. Instead of repeatedly constructing strings, this method involves directly iterating through the sequence to count matches using a fixed size window. While this avoids string construction and can be more memory efficient, it is less intuitive and adds implementation complexity. Among these options, the binary search approach stands out as the most efficient and elegant. It leverages the monotonic property of substring repetition to minimize computation while being straightforward to implement. This makes it the preferred choice for solving this problem. With any algorithmic approach, trade-offs must be considered. While binary search requires an understanding of the monotonic property of substring repetition, its efficiency far outweighs the simplicity of brute force. The sliding window approach, on the other hand, avoids the need for string construction but introduces additional implementation complexity without offering significant performance gains over binary search. Ultimately, the binary search approach strikes the best balance between simplicity and efficiency. It minimizes the computational overhead by reducing the number of substring checks and avoids unnecessary operations, making it well-suited for handling large inputs. In conclusion, leveraging the monotonic property of substring repetition through binary search ensures that we achieve an optimal solution to the problem of finding the maximum repeating substring. The problem we're solving here is to determine how many times the string word can appear consecutively as a substring within the string sequence. Consecutively means that the instances of word must be contiguous and directly follow one another without any gaps. For example, in the string sequence equals abababa and word equals aba, the result would be 2 because the substring aba appears twice consecutively. The first occurrence starts at index 0, and the second starts at index 2. To solve this, the key idea is to slide the word across the sequence and count how many times it repeats consecutively. This requires careful handling of overlapping substrings to ensure we only count valid consecutive repetitions. Let's break down the approach step by step. One initial approach we can consider is the brute force method. Here's how it works. We start at the first index of the sequence and check if the substring starting at the current index matches word. If it does, we slide word forward by its length and continue counting consecutive matches. If we encounter a mismatch, we reset the count and move to the next starting index to try again. Throughout this process, we keep track of the maximum count of consecutive matches we've seen. Once we've checked every possible starting position in the sequence, we return the maximum count. While this method works, it can be inefficient because it repeatedly checks overlapping substrings. To address this, we can optimize the approach using a sliding window technique. In this optimized method, we initialize variables to track the maximum consecutive repetitions, the current streak, and our position in the sequence. This approach reduces redundant checks and improves efficiency. Now, let's discuss how the optimized sliding window approach is implemented. First, we iterate over the characters in sequence using an index I. At each step, we check if the substring from I to I plus len, word, matches word. If there's a match, we increment the current underscore count by 1 and move the index I forward by the length of word. This ensures that we're checking only for consecutive, non-overlapping repetitions. If no match is found, we update the max underscore count to the larger of the current max underscore count and current underscore count. Then, we reset current underscore count to 0 and increment I by 1 to check the next character. After the loop ends, we perform one final update to max underscore count to account for any streak that may have continued until the end. Finally, we return max underscore count as the result, which represents the maximum number of consecutive repetitions of word in sequence. There are a few key insights that make the sliding window approach efficient. First, by moving the index I forward by the length of word during consecutive matches, we avoid redundant checks, which significantly reduces the time complexity compared to the brute force method. Second, we must consider edge cases. For instance, if the length of word is greater than the length of sequence, the result will be 0 because word cannot fit inside sequence. Similarly, if either sequence or word is empty, the result should also be 0. Another important case is when sequence contains multiple non-consecutive instances of word, in which only the longest streak of consecutive repetitions is counted. Finally, it's worth noting that this approach does not require any additional data structures beyond simple integer counters and string slicing, making it both space-efficient and straightforward to implement. Let's analyze the complexity of this sliding window approach. In terms of time complexity, the worst-case scenario involves iterating through the entire sequence once, with each substring comparison taking constant time. This gives us a time complexity of O(n), where n is the length of sequence. For space complexity, the algorithm uses only a few integer variables to track counts and the current index. Since no additional data structures or storage are required, the space complexity is O(1). To make these concepts more tangible, consider an example where sequence equals abababa and word equals aba. We'll now walk through how the algorithm processes this input step by step to find the maximum consecutive repetitions. Here's how the algorithm executes for the given example. We initialize max_count to 0, current_count to 0, and I to 0. In the first iteration, the substring sequence 0 to 3 equals aba matches word, so we increment current_count to 1 and move I to 3. In the second iteration, sequence 3 to 6 equals aba also matches word, so we increment current_count to 2 and move I to 6. In the third iteration, starting at I equals 6, there's no match because the substring at this position is not word. At this point, we update max_count to 2, reset current_count to 0, and move I to 7. Since the loop ends here, we return max_count, which is 2. This means that the maximum consecutive repetitions of word in sequence is 2. This example demonstrates how the algorithm efficiently handles consecutive matches and ensures accurate results. This solution is concise and leverages the ability to check for substring matches directly in Python. Here's the detailed explanation. 1. Initialize k to 0. The variable k will keep track of the maximum number of times the word can repeat consecutively in sequence. 2. Use a while loop to check for consecutive repeats. The key part of the logic is the condition word asterisk, k+1, in sequence. This dynamically constructs a string by repeating word, k+1, times and checks if it exists as a substring in sequence. 3. Increment k if the condition is true. Each time a repeated substring is found, k is increment to test for the next possible repetition. 4. Terminate when no further repetition is found. Once word asterisk, k+1, no longer exists in sequence, the loop stops, and the maximum value of k is returned. This approach avoids unnecessary computations by directly checking for the existence of repeated substrings, making it efficient and straightforward. The function handles edge cases such as when sequence or word is empty, or when word is longer than sequence, returning the correct result of 0 in these cases. The algorithm runs efficiently for typical input sizes, as Python's string operations are optimized for performance. This is the Java implementation of LeetCode problem number 1668, maximum repeating substring. The logic mirrors the provided Python solution, using a while loop to check if the word repeated, k+1, times exists in the sequence. The Java-specific string.contains and string.repeat methods are used to replicate the behavior of Python's in operator and string multiplication. The code is concise and leverages Java's built-in methods effectively. To solve this problem, we start by analyzing the first example where the input sequence is a babk and the word is ab. Initially, we set k to 0, which represents the count of how many times the word can repeat consecutively in the sequence. We then calculate the first repetition of the word, which is simply word asterisk, k+1, giving us ab. Next, we check if this result, ab, exists in the sequence. Since it does, we increment k by 1. Now, the next repetition we check is ABAB, calculated as word asterisk, k plus 1. This time, ABAB is not found in the sequence, so we exit the loop. The final value of k is 1, which means the maximum number of times AB can repeat consecutively in a BAB is 1, and that's our output. Breaking this down further, we can observe the intermediate states for this example. At the very start of the loop, k is initialized to 0. After the first iteration, where we find one repetition of AB, k becomes 1. Finally, the loop ends as ABAB is not in a BAB, leaving k at 1. Now, let's look at a slightly more complex example where the sequence is ABABABAB and the word is AB. Again, we begin by initializing k to 0 and calculate the first repetition of the word as AB. Checking the sequence, we find that AB is present, so we increment k to 1. The next repetition is ABABAB, calculated as word asterisk, k plus 1. However, ABABAB is not found in the sequence, so we exit the loop. The output for this example is also k equals 1. To summarize the intermediate states for this second example, we start with k equal to 0. After finding one repetition of AB in the sequence, k is increment to 1. The loop then ends when ABABAB is not found, leaving the final value of k at 1. Now, consider an example where the sequence is ABABAB and the word is AB. As before, we initialize k to 0 and calculate the first repetition of the word, which is AB. Checking the sequence, we find AB, so we increment k to 1. This leads to the next repetition, ABAB, which is also found in the sequence, so k is increment to 2. These steps will continue as long as the calculated repetition exists in the sequence. With the sequence ABABAB and the word AB, we proceed to the second iteration where ABAB is found, so k becomes 2. The next repetition, ABABAB, is also found, so k is increment to 3. Then, we check ABABAB, which is still in the sequence, leading to k being increment to 4. Now, the next calculated repetition is ABABABAB, which is not in the sequence. At this point, we exit the loop. The final output is k equal to 4, indicating that AB can repeat consecutively up to 4 times in ABABAB. To recap the intermediate states for this example, k starts at 0. After finding one repetition of AB, k becomes 1. With the second repetition, it increases to 2. After the third repetition, k is 3. After the fourth repetition, k reaches 4. Finally, the loop ends when ABABAB is not found, leaving the final value of k at 4. This means the maximum number of consecutive repetitions of AB in the sequence ABABAB is 4, and that's our result. This approach efficiently calculates the maximum repeating substring by iteratively checking for consecutive repetitions until the pattern no longer exists in the sequence. To analyze the time complexity of the solution for the maximum repeating substring problem, we start with the outer loop. This loop continues to execute as long as the constructed string word asterisk, k plus 1, is found in the input string sequence. Here, n represents the length of sequence and m represents the length of word. In the worst-case scenario, the loop will run approximately n/m times, which corresponds to the number of times the word can repeat within the sequence. Within each iteration, the operation word asterisk, k plus 1, involves string multiplication. The time complexity of this operation depends on the length of the resulting string, which is k plus 1 asterisk m. Therefore, string multiplication in each iteration takes k plus 1 asterisk m time. Finally, the substring check, performed using the and operator, determines whether the constructed string is part of sequence. While naive substring search can take n time per iteration, Python optimizes this with advanced algorithms like Boyer-Moore or Ravenkarp, making the search more efficient. However, for simplicity, we approximate this step as n per iteration. Now let's consider the overall time complexity. In the worst case, the while loop executes n/m times. For each iteration, the operations include string multiplication, which takes k plus 1 asterisk m, and substring search, which we approximate as n. Combining these, the overall time complexity can be expressed as n/m asterisk n plus k plus 1 asterisk m. Simplifying further, the worst-case time complexity becomes n squared/m, because k can grow up to n/m in the worst case. On the other hand, in the best case, if the word is not found at all in the sequence, the loop exits immediately, resulting in a best-case time complexity of O(n). Shifting to space complexity, we begin by analyzing the temporary memory usage. String multiplication, as seen in word asterisk, k plus 1, creates a new string of size, k plus 1, asterisk m in each iteration. This temporary string contributes to the memory usage. For substring search, the AND operator itself operates directly on the existing strings without requiring additional space proportional to their size. When we consider the overall space complexity of the solution, the primary contributor is the temporary string created during the word asterisk, k plus 1, operation. The size of the string can grow up to k plus 1, asterisk m, where k reaches its maximum value of n/m in the worst case. This means the largest string in memory can be proportional to the size of the input sequence, resulting in an overall space complexity of O(n). To understand the efficiency of this approach, let's compare it to a naive solution. A brute force method would involve checking all possible substrings of sequence to identify repetitions of word. This would require generating all substrings, leading to a time complexity of O(n cubed in the worst case. In contrast, the optimized approach avoids this inefficiency by directly constructing repeated strings and using efficient substring search algorithms. This reduces the time complexity significantly, making the solution much more practical for larger inputs. To summarize, the optimized solution for the maximum repeating substring problem has a worst-case time complexity of O(n²/m) and a best-case time complexity of O(n). The space complexity of the solution is O(n), driven by the temporary string created during the word asterisk, k plus 1, operation. This approach is substantially more efficient than a brute force method, which would have a time complexity of O(n cubed). By leveraging string multiplication and optimized substring search algorithms, the solution avoids redundant computations and achieves better performance for larger inputs. This makes it a practical and efficient approach to solving the problem within reasonable constraints. When solving the maximum repeating substring problem, there are a few common mistakes to be aware of. First, it's easy to miscount overlapping substrings. For example, in the sequence ababab and the word abab, the second occurrence of abab overlaps with the first. To handle this, you can use sliding window or string manipulation techniques that explicitly account for overlaps. Another common pitfall is relying on inefficient brute force implementations, where you iterate through every possible substring and check for repetitions one by one. This approach can lead to O(n²), or worse time complexity for large inputs. Instead, you should optimize using efficient string search algorithms like FIND or the Knuth-Morris-Pratt (KMP) algorithm. Additionally, don't forget to handle edge cases properly, like when the word is longer than the sequence or when the word is an empty string. These scenarios can lead to unexpected errors if not addressed explicitly at the start of your function. Lastly, be careful with boundary conditions in your loops. Off-by-one errors are common when iterating over substrings, so it's important to clearly define the range of indices your loop should cover and validate your implementation with test cases. Another mistake to watch for is ignoring case sensitivity. Some may assume the problem is case insensitive without explicit clarification, treating word and word as equal. Always read the problem description carefully and ensure your code respects case sensitivity. If normalization is required, methods like .lower can help. Now, from an interview perspective, this problem falls under the category of substring search, which is a common theme in technical interviews. Efficient solutions often involve algorithms like KMP, Rabenkarp, or simply leveraging built-in string search functions like FIND. The sliding window technique is another key strategy that can reduce complexity in substring-related problems. By maintaining a window over the sequence, you can avoid redundant computations. Additionally, breaking the problem into smaller steps, locating instances of the word, counting repetitions, and combining results can help ensure clarity and simplify debugging. Lastly, never hesitate to ask clarifying questions during interviews. For example, confirm whether overlapping substrings are allowed, whether the problem is case-sensitive, and what constraints might exist, such as the maximum size of the input. This problem also connects to several related problems on LeetCode, which can help deepen your understanding of substring operations. For instance, LeetCode 28 asks you to find the index of the first occurrence of a substring in a string, a classic problem in string search. LeetCode 459 looks at whether a string can be constructed by repeating a substring, while LeetCode 686 finds the minimum number of times a string must be repeated to contain another string. Finally, LeetCode 796 explores whether one string is a rotation of another. These problems share overlapping concepts that can reinforce your skills in pattern matching and repetition. In terms of alternative approaches, the sliding window technique is simple to implement and generally effective for smaller inputs. However, it can still result in n² complexity in certain cases, especially if nested loops are required. The KMP algorithm is far more efficient, operating in n+m time, but it requires a solid understanding of prefix tables and can be more challenging to implement. Finally, you can use greedy search methods with built-in functions like find in Python or indexOf in Java for quick solutions. While these methods are fast and easy to implement, handling overlaps may require extra logic. Each approach has its trade-offs, so choosing the right one depends on the problem constraints and your familiarity with the techniques. Great work on completing the problem. To summarize, we explored how to determine the maximum number of consecutive repetitions of a substring in a sequence. We discussed the iterative approach and its computational complexity. Keep practicing similar string problems to sharpen your skills. Remember to like and subscribe for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!